Good afternoon, everyone. Welcome to the webinar. My name is Inas Sheikh, and I will be your co-host today. Before we get started, please let me take a few minutes to introduce EXPLIoT. EXPLIoT is an open source framework for IoT security testing and exploitation. It is the product of our experience and expertise in IoT security. At EXPLIoT.io, we build IoT security tools and target vulnerable devices for professionals and people who want to get into IoT security. We have cooked some amazing products in our labs. A few of them are EXPLIoT.io, an advanced hardware lab equipped with best tools and equipment performing security evaluation of hardware and IoT devices. We also have an online store where you can find all our IoT security creation and other cybersecurity hardware. Hello.
Yes, now you're audible.
Okay, so I will start again. I'm so sorry for that. Welcome everyone and good afternoon. My name is Inas Sheikh and I will be your co-host today. Before we get started, please let me take a few minutes to introduce EXPLIoT. EXPLIoT is an open source framework for IoT security testing and exploitation. It is the product of our experience and expertise in IoT security. At EXPLIoT.io, we build IoT security tools and target vulnerable devices for professionals and people who want to get into IoT security. We have cooked some amazing products in our labs. A few of them are EXPLIoT.io, an advanced hardware lab equipped with best tools and equipment performing security evaluation of hardware and IoT devices. We also have an online store where you can find all our IoT security creation and other cybersecurity hardware. We have cooked CloudFuzz. It is a scalable and distributed fuzzing platform designed to facilitate fuzzing for open and closed source application on various platforms. IoT Auditor, an IoT security compliance testing and vulnerability management platform that empowers engineers to test and analyze different attack surface the IoT ecosystem like radio communication, firmware, hardware, IoT cloud. We are sharing the community edition link on the chat box. You can also scan the code on the screen to access it. Today's webinar is on IoT hardware hacking, SPI hacks. SPI is one of the most popular high-speed protocols in an IoT product. If you use memory chips and RF modules, you will encounter SPI protocol. In this webinar, we will cover basics of SPI protocol, security issues with SPI protocol, how to find out SPI pins on an IoT product, how to use EXPLIoT tools to identify SPI pins, sniff, and hack SPI chips. Today, Mr. Yashodhan, IoT researcher and compliance manager, will take us through IoT hardware hacking. You can read about his beautiful accomplishment on this slide. At PIO2, Mr. Yashodhan is responsible for security assessment and creating threat models for IoT protocols. He is also working on achieving security certifications and accreditations for the organization. His current IoT security research focuses on side channel attacks and fault injection. Before I hand it over to Mr. Yashodhan, I request you to follow a few housekeeping etiquettes. Please be on mute. If you have any question, write it on the chat box. We will answer it at the end of the webinar. We will be releasing the recording of this webinar on our social handles. Make sure you are following us. If not, you can click on the link on the chat box and direct yourself to our social handles. Now, without further ado, let's get started. Mr. Yashodhan, over to you.
Thank you, Inash. So let me share the screen. I hope that's visible.
Yes.
Okay. So welcome everyone to this SPI Hacks webinar. The idea over here is to discuss about some of the fundamental aspects of SPI, how we can use the SPI in different products, how we configure them, what is the basis of existence of this SPI, why do we need them. We'll also look into some of the critical aspects of SPI in terms of the security, where we'll see some of the attacks that has happened on some of the SPI chips. And later we'll see a practical demonstration of how the SPI can be attacked. So let me start with the presentation. So in the beginning, let's have one of the important features of this SPI. So if you are worked with any embedded system design, I'm sure you must have interfaced some sensors, the SD card, or any of the RF modules. Of course, we use this SPI protocol for that. SPI stands for Serial Peripheral Interface. It is a kind of a master-slave communication. It has a synchronous kind of serial communication. We'll discuss all these points in detail. I'm just noting and discussing the key aspects of SPI. Whenever we interface the SPI, the main thing is on the transmitter and the receiver, there are different shift registers over there, and they are responsible for such kind of high-speed communication. Then the other advantage of this SPI is they can use it for multiple peripherals. It is also called as a no ACK protocol, meaning it does not need kind of an acknowledgement from the slave to the master if there is communication happening. And it's being used widely in different embedded peripherals though. Now, first, let's understand why are we going for such kind of serial peripheral interface communication. To begin with, when we go for the different embedded communication protocols, the very fundamental of them is the UART protocol, Universal Asynchronous Receive Transmit. We had covered this particular UART protocol in the past seminars. Now, when we use that UART communication, what happens is, on the left side, you can see it's kind of a asynchronous communication. It means we do not have a kind of a reference clock between transmitter and the receiver. As you can see over here, is like when the transmitter wants to communicate to the receiver, both have to align at certain baud rates. So if, let's say, a transmitter is transmitting at, let's say, 9600 bauds, the receiver has to receive at the same speed. If it is on a higher, on a lower side, what will happen is you'll get a garbage data. The reason for that is the receiver will be sampling this particular bits at different rates, and that is resulting into this garbage of the data. So what happens in UART communication is like the transmitter, let's say, want to transmit something. First, it will send a start bit. So the receiver knows, okay, I'm going to get something now. So once it receives the receive bit, then you have the 8 bits of data. And once you have the 8 bits of data, you have a start bit, meaning you have sent a byte. And this cycle repeats for each and every byte sent over there. Now, eventually, the disadvantage of that is, though this is very simple protocol, straightforward protocol, what happens over here is you are adding the extra overhead for these bits. So at every bit byte ahead, you're having a start bit. And once your byte is completed, you are sending a stop bit again. So that way, this is kind of an overhead over there. But when you go for the higher systems, each and every peripheral, which is have the computational capabilities, right, has certain clock. And if that clock is synchronized between the two modules, it will ease out the communication. And the same concept has been used in SPI. So here on the right hand side, you can see the synchronous communication. Synchronous simply means we are working on the same clock. And the same data, if you can see over here, just comparing these two data, on the left side, you have start and stop bit, additional data. On this right side, you have the clock on which your data has been synchronized. Now, this has been in a need when you have a high-speed communication or when you need multiple peripherals over there, you need such kind of communication. So that is the one thing. Now coming to the SPI protocol. As we said, it stands for Serial Peripheral Interface. It had been developed by the Motorola, and it has the 4 fundamental signals, right? So all those peripherals who has the capability of SPI communication has these 4 utmost pins at their peripherals. The first is the MOSI, which stands for Master Output and Slave Input. This is called, since this SPI communication is the master and the slave communication, the master is always has the control over there. So here MOSI is the one where the master will send out the data and slave will receive the data. And the vice versa is called the MISO, where slave wants to communicate and a master want to receive the data. Next is about the serial clock. As it's a synchronous communication, we need a common clock between them. So as you can see over in this particular figure, you have this multiple slaves connected, and each slave has been connected separately, and you have the common clock over there. So all those slaves connected are sharing the clock from the master. So master is the one who will generate this particular serial clock. Then you have something called as a chip select or slave select. So this is basically the extra hardware pin, the physical pin over which you are connecting this particular device, or you can say the slave is connected on that slave select pin. Generally, it does not happen in terms of the UART. We have the RX, TX different channel. That's it. If you go to, let's say, another communication kind called the I2C, where you do not have a specific kind of slave select. There you have basically a synchronous clock and only the data channel, only 2 channels over here. But this is exclusively from the perspective of the high-speed communication. You have these 4 channels. So this will give an idea why this can be considered as more in terms of the high speed, because you have complete duplex channel available for you, the MOSI and the MISO part, and you have a synchronous clock for that. So these are the fundamental pins when we come to any of the SPI protocols. Now let's understand in detail about this typical master and slave communication. The SPI though has the full duplex capacity. On the top part, you can see the master and the slave. As you can see clearly in all those figures that the master has the SPI clock generator. So always remember, the master is going to generate the clock. The slave is not responsible for generating the clock. And both of them has the shift registers. Right? So the shift registers are nothing but basically the combination of gates where you have those sequential logic and you're pushing the data over there. Right? So these have the typical receive and transmit shift registers over there. Now, where are these connected? So you can see the receiver is basically connected to MISO part, where you have the inputs coming, and the MOSI part is basically the output of the master, and it is exactly opposite on other side, where on the slave part, the MOSI is connected with the receiver shift register and MISO is connected with the TX shift register, meaning the data that has been transmitted by the master is basically received at the receiver and vice versa. So these are the important consideration when we look for any of the SPI designs. And at the bottom, we can see about this NSS. This is basically the slave select part. So these are the 4 physical pins on this device. And here you can see it's a full duplex communication where master can send a data and slave can send the data at the same time. Simultaneously, they can work on that. Right? So this is the one of the fastest communication. We have a full duplex. Then coming to the next part, where you have the half duplex system, where with the same SPI pin, you can make it as a half duplex, and eventually, as you can see over here, is like the RX and TX shift register have been short, right? So which makes it to the half duplex part. So at instance, if master is transmitting the slave has to receive. If a slave is transmitting, master has to receive. Then we also have something called as simplex communication, where only master is responsible for sending the data. So as you can see over here, there is no communication from the slave part. It is only the master who is sending the data. Then there is another combination called as a multi-master combination, which you can see over here. So what do you mean by multi-master communication? As you can see in this figure, this master and slave, the written as each master can be a slave and slave can be a master, meaning they can alternately become master and slave depending on the use case. So for example, let's say this particular peripheral A and peripheral B wants to communicate at particular instant of time. The A wants to be master, then B can be a slave. And then the full duplex communication can happen as shown in the first figure. But if we want to change the roles, right, we can still do that here with the help of these GPIOs. So if you note the differences between the three figures compared to the fourth one, you can see those slave select has been used for the GPIOs, where your GPIO has to set or reset depending on what type of role that you are playing. And this will consider as a master slave, the multi-master communication. Though it has been rarely used, what I've seen in this thing, but still that capability is initially I haven't seen when you go to the typical 8 bits of microcontrollers where he's has capabilities, but with the advent list ARM Cortex M4 and those designs, all expressive designs, you have those capabilities available over there. This is the type of a master-slave communication. Then we still have a multi-slave communication, right? Where, as you can see over here, we have a single master and you have a multiple slaves. Right? So it is again can be a full duplex, simplex, or half duplex communication. The difference over here is like all the 4 pins, the MISO, MOSI, the SCK pins, they can see they are the common between all of them. So whatever that is coming out from the master has been shared commonly with all the slaves. Where is the change? The change is between the NSS, or what we call as a slave select. So for this matter, we have the dedicated slave select for each and every slaves. And you can consider these are kind of a GPIOs on your master part. So the thought process is like, if let's say your microcontroller has 2 basically, let's say there is a single SPI enabled peripheral over there. But if you can make multiple slave selects on your GPIOs, right, you can have the multiple SPI communication on your pin. The reason being, you can have these 3 MISO, MOSI, and SCK common, and the slave select can be a multiple channels that you can use from that. Right? So this is something very, very basics about the SPI communication, the architecture of the SPI communication. Okay? Now let us understand what this SPI protocol, how does that work? So we say that this is a synchronous communication. So the clock of this particular communication plays a very, very important role during all the transfer of the data. So over here in this particular figure, you'll see some word like CPOL, CPHA. So this CPOL stands for clock polarity and CPHA stands for clock phase. So here polarity means what? So if you say that clock CPOL equals 0, meaning that you have the rising edge, the typical rising edge, like the clock polarity, the one is considered high, and that way we can consider as a standard signal over there. When you have invert this particular polarity with this sending the bit of CPOL equal to 1, you have the reverse polarity of that. So this is the one way of addressing the clock part. So this is the inverting and non-inverting clocks that we have is the first important feature when we go for the serial peripheral interface communication. Another part over here is about the phase of the clock. Okay? So now if you observe this particular phase of the clock, what you see is like just comparing the this particular clock, and along with that, if you see this particular 8 bits of data, if you observe, let's say whenever the CPHA is 0, you can see it has been sampled not at any particular instant of time. It can be communicated at any instant of duration. But eventually, if you go for the CPHA1, you will see whenever there is either a rising or a falling edge is there, right? You have this particular communication to be begin. right? So it is exactly working at those edges, right? So the data is being transferred, each bit is being transferred at the rising or falling edge of the clock, right? So depending on rising or falling edge and what type of phase we are using, there are different modes that we'll see in the next slide. But if you observe here, it's basically simple. The difference between the CPHA 0 and 1, as you can see, the data basically it has basically what you can is a shifted in a time domain. It is just a simple thought process. So one important consideration is the polarity, inverted or non-inverted, and second is the shifting of this particular signal in time domain itself. Right? So as you can see over here, these are the shifted in time domain with few nanoseconds kind of a delay over that, right? So this is used again for the synchronization purpose. Now, based on such combinations, we have the modes of the SPI, right? So the mode 0, where we say the clock polarity 0 and the clock phase 0, meaning, let's go back again. So when we have this combination of the clock in a non-inverting way, right? And you have the clock phase 0, meaning you are basically choosing starting at this particular instant of time, and then you do not have you do not sample this particular data at either a rising or a falling edge of the clock. Right? So that is the mode 0 over there. Coming to mode 1, where you have the clock polarity as a non-inverting and the clock phase of 1, again meaning if you just compare clock polarity 0 and the clock phase. So over here what happens is exactly at the rising edge of your signal, you are sampling the data. You're sampling data. Ideally, SPI had been considered for the 8 bits of data, but with the latest STM32, or if you say the expressive microcontrollers, they're still going with a complete word size of a data communication over there as well. So similarly, other like mode 2, 1, 0, the clock polarity is now inverted and the clock phase is 0, that basically time shifted. And mode 3 is again there 1, 1. So basically you have the inverted clock as well as the phase is again a shifted one. So just to observe, the mode 0 and mode 3 will be actually opposite to each other, completely opposite, and mode 1 and mode 2 will be opposite to each other. So basically they are nothing but the NOR logic that we use, and this is happening through basically the shift registers over there. Is it as simple as that in a digital logic sense? So this is how we are communicating, and this is how you are having a MISO and MOSI communication. You are storing data in shift registers and sending over there. Serially, you are sending over there. So I hope the communication, let me again revise this particular. So the always remember, master is the one who selects the slave, and then the master will initiate the clock signal. So what I'm discussing, the steps in which the communication will begin. So master will select the device, then it will set up the clock, right? Master sends the data on the MOSI line, and the slave sends the data on the MISO line. So once the master is selecting the clock signal, the communication begin. So then you have a combination of whether you have the slave select to be the active low or active high. Most of cases, you will see the slave select as the active low, and in a rare case, I've seen it is active high though. Now, let us understand where are basically these SPI protocols has been used. Okay? So that it will give an understanding. So I hope most of you have gone through, if you're from the embedded or IoT field, you must have gone through all these typical peripherals. Possibly someone has interfaced that. So if you see the RF transceiver, the one of the famous from the Nordic NRF-L01, this is basically a radio frequency transceiver used for some of the like a kilometer or so range for all kind of a mid-distance region where you have some of the data to be communicated. The idea here is they have their own shock burst protocol, but the communication speed and the bandwidth they're giving is really high because it's a RF range communication. And to deliver that amount of data, you really need a kind of high-speed protocol. The reason being because let's say you are getting a data from the sensors, right? You want to share that data or transmit that data over this particular radio frequencies, right? Eventually, let's say you gather 8 bits of data, you want to push it over there. Now you need a high-speed communication between your microcontroller from where you have a sensor acquisition, and then you want to push a data to the peripheral of the RF. So you need the in between your others high-speed communication, for which SPI is one of the ideal solution for that. So again, CC1100, which is on the similar lines by the Texas Instrument, they have been used again the SPI protocols. In many cases, what people generally does is, if you don't want to use this type of protocols, they convert this SPI protocols to the UART part, and again you send only the RxTX data. That's what people are also doing. Then coming to different sensors. So the sensors I mentioned were like LIS3DH12 or IS3WB. These are the typical accelerometer and the gyroscope sensors used for kind of a predictive maintenance. So let's say if I want to take a data from machinery, the accelerometer, these are basically the accelerometers, and I want to take a data from the three-dimensional space, like the three axis, XYZ axis of the accelerometer. I want to take a data from the vibration of the motor. So what I'll do is I need the again high speed of the communication, where the motor are operating at a high speed, right? Higher RPMs. Again, I'll prefer to have a SPI communication for that as well. Then coming to the memories, there are standard SPI flash memories. So like W25, Q128, like the 128 here means that 120 megabits of data, the storage memory, and it is a typical SPI communication, SPI NOR flash, where possibly you'll put some data, or you can store your firmware as well over there. Then there is called a CY15 series of, this is called as a FRAM, ferroelectric RAM. This is more specifically used in different scenarios where like in a petrochemical industry, nuclear industries, where you need kind of a longer life of read and writes, right? But the reason we are using the SPI here is like there will be n number of read and writes between microcontroller and your peripheral, and hence we knew that this high-speed communication over there. And of course, like I'll discuss about this security measures of the memory in few next slides. So just go ahead. Now, how we can look into the attacks on the SPI? So the one way we can look on the attack is like the sniffing. So simply you have, let's say, sensors and or any peripheral for that matter, and you have a microcontroller or any of the computing system, and you have the SPI communication. So what you can do is you can take a logic analyzer, right? Connect those 4 lines, MISO, MOSI, select, and a clock, and you can use typical this logic analyzer software, and you can analyze the data. Right? This is way of sniffing. We'll understand what type of communication happening, meaning what type of data is being transmitted. You can sniff the data as well. That's the first part. Then you can go for the tampering of the data. Once understand these things, then you can basically read and write and send, and you can change the command as well. So if you remember about the master-slave communication, you can attack on that as well, changing some of the bits and manipulating the data. Then the data extraction part, which of course very important. Let's say in the memory you have important data, and you can use go to that particular memory location of the SPI. You can sniff it, or you can just extract the data by using certain utilities of that. Right? I remember this particular case where I had this kind of FRAM over there, and there was a security link when the product was reviewed. It was told that you have to store this particular data and 3 different locations in the same memory, and you have to check for something called as a TMR check. TMR stands for triple modular redundancy, meaning let's say if I have a same data at location X, Y, and Z in the same memory, what I'll do is while reading the data, I'll take the data from all these 3 locations and do the XORing of that, right? So eventually, with the majority of votes, which has the highest vote of data, will be selected as the correct data over there. And we have this data manipulation, meaning let's say if I'm able to access the data or any of the firmware from the memories, the SPI memories, you can actually write it back over there. So these are the possible attacks on the SPI over there. So let's look into some of the cases where these type of attacks that has been happened, right, which are publicly available. I'll be discussing those things as well. So if you see this particular chip like FL128PF, right, this is kind of a memory chip. As you can see, there are some specification I have mentioned, right? 120 megabits of the memory. and it has the options of like 256 KB of sectors or 64 kilobytes of sectors over there. As you can see in this particular, basically this memory has been residing into some of the routers, and you want to extract the kind of a firmware of this particular router. So the idea over to start with, so what an attacker can think of is like, let's go back and check a data sheet of this FL128. Once he finds the data sheet of this thing, of course, you will see in the pin diagram in between that, right? So in the pin diagram, these are some of the important pins that you can see: slave select, serial clock, MISO, MOSI, right? Slave output, slave input here. So MISO, MOSI can be, addressed DO, DI in different way. So one has to better understand these terms when you go to the SPI. Yes. Yeah. So then you have some hold pin. The idea behind that is like whenever there is a communication happening, it can pause any kind of a serial communication. There are many challenges when you try to extract this particular memories, and the hold pin plays a very important role. So majority times people leave it blank, and then you won't able to get any kind of data. So in most of the cases, we observed that you set that particular to the VCC, basically a logical high, and then you're able to extract the firmware from that as well. So with this particular thing, the case happened is like, so you have basically this pins connected to your some of the master device, and you, let's say here the considered like Raspberry Pi, right? And the Raspberry Pi, you have these particular SPI pins, you connect to those memories and use some tools or utilities called as a flash ROM, and with you can basically specify which type of SPI peripheral from the Raspberry Pi you're using. You can set basically the speed 8008 kilohertz of the frequency over there, and basically you can use this utility and dump this particular firmware, right? You can write this firmware to your Raspberry Pi systems. So there can be certain challenges in terms of setting up the frequencies. So at certain times you'll fail or those things there, but still setting up some hardware pins and putting a right command will make sure you get a right firmware over there, right? To verify you have got the right firmware is like you can do it multiple times over there, right? So as you can see, as you can see over here, the same firmware with a different name, but just you can just verify the checksum, like this is a SHA-1 sum, and you get this the same value of the SHA-1 sum for this particular data, right? So SHA-1 is like the hashing part. So if you have the same data, you will get the same hash for the same data. So it means that all the binaries are of the same value. So you can just verify on that as well. Right? And then once you dump this particular binary, right, then you have the multiple tools to analyze the firmware, whether it's a string or a bin walk or any kind of Gidra. So that depends on how deeper you want to go and analyze your firmware part. Now let's understand another type of attack on a TPM. So TPM basically stands for a trusted platform module. Similar to the different crypto chips we use for authenticity. This is again used for the authentic communication. And this particular case I'm discussing is about the BitLocker that we use in the Microsoft. So this Infineon chip, this is TPM SLB9665. And as you can see, this is the TPM, this is the flash, and there can be the multiple controllers and peripheral over there. Right? But the idea here is to attack this particular TPM. The challenge over here is the TPMs being the trusted platform, like you have the certain capability of the cryptographic functions. So most of the TPM, if you just take, they will have the capabilities typical like SHA-1, SHA-256, they can support AES-256 likewise. And eventually you have the authentic communication between your system host and this particular peripheral. Generally, if you go for, let's say, secure boot kind of things, right? When you want to go for an authentication system, right? You use that particular system. Okay. So what people have done is like they wanted to extract this or sniff this particular TPM. Okay. And even if we have also tried this particular attack for different peripherals. The challenge over here, what happens is like there is a digital signature being communicated between this TPM and your host device. Right? So that way you cannot sniff in, you won't understand what things are there, right? It's very cryptic kind of stuff. One of the things, like if you go detail into this particular data sheet, you'll find some of the loopholes over there. So what is the loopholes? So as you can see mentioned, TPM data FIFO. So this is particularly kind of a buffer where you have certain this cryptographic keys, right? The decryption keys for this particular data. And if you're able to tap into this FIFO part, right, we'll able to get the keys. So as you can see over here, this is kind of a cryptographic key one has to got. So as you can see, 2C00, right? Likewise, they have started getting this decryption keys, right? So still there are many things. Just on the other part, you can see, since we are focusing on the SPI part, you can see that this particular is working on the SPI peripheral. Sorry, I forgot to mention that it's a SPI enabled chip. And you can see the clock, the SPI enable, the MISO MOSI. So here enable is nothing but your clock, the chip select part over there, right? So these 4 pins, and you can see this communication big happening. So on the next part, this is the another way they have, find out this particular FIFO data. So it has been in the parts. And likewise, multiple things when you find, so you can actually go and find out the complete decryption key. So for example, if you join this 2C000, then come to 011000, the next part of whatever the mentioned over here, and the final part 0888 whatever, and the last part, right? If you combine all those things, that is your basically the decryption keys for that. This was actually meant when you got it, and then you can sniff the communication and understand, you can actually decrypt the data as well. Right? So this has been happened on the BitLocker that we generally use in a Microsoft. Right? So to encrypt your what you call as a hard disk encryption part. So you can actually decrypt data if you just sniff into this kind of TPM. So now, what are the tools used for this particular framework? Right? So there are certain hardware tools and there are certain software tools as well, right? So EXPLIoT Nano is our own tools that we have designed. Then we have CS341, and then you have typical like software tools, the EXPLIoT framework. We have the plugins for SPI as well. In that, we'll be seeing the demo of that along with the EXPLIoT Nano as well. Right? So you'll get to know how these plugins work by the side. And the flash ROM, if you remember, in the first case, when we extracted the data from the memory, we use the flash ROM as well. And there are different tools happening, right? So even you can use the Raspberry Pi or BeagleBone back to use this particular tool, right? Now let's see what type of attack can be possible through this particular EXPLIoT Nano as well. This particular EXPLIoT Nano is a kind of a multi-purpose, multi-protocol hardware device. It supports the standard UART communication. You can use it, like, let's say if you want to hack into UART, you can use this particular tool. And there are certain utilities where you can find the baud rate of the communication. You can access the data first way. Same thing with the SPI. It can use SPI, like it can sniff, not sniff, basically it can extract data from the SPI with certain utilities. Then same, you can do it with I2C as well as SWD or a ZTAC. So this particular EXPLIoT Nano supports all these multiple protocols in a single device itself. Now we'll see kind of a demo where we'll extract some of the firmware from certain SPI flash, right? So before I start the video of that, what we have done is, like, since the process is a bit tedious, we have recorded kind of the steps in which this can be done, right? And we integrated that and we'll be showing you that demonstration. And while playing the video, I'll be telling, okay, at this instant, this is happening, at this instant, this is what happening over there. Right? But before going over there, this is the connection that is being used over here. So you can see this kind of a SPI flash has been used. So there is a serial clock, right? Then you have a chip select part, right? Then you have data out and data in. So the MISO and the MOSI part of it. But again, we have this hold pin, which is again needs to be connected to this particular high voltage, if I remember. Otherwise, you won't able to extract the data over there. These are the pinouts. At the bottom, you can see those 12 pins. These are nothing but the output of the EXPLIoT pins. On the bottom, GG stands for the ground. V stands for the different voltage that you're working on. and these are the actual communication pins where you are communicating. So you can see the MISO, the MOSI, then your clock and the slave select. These 4 pins have been communicated from the Nano to this particular flash over there, right? So without further ado, let's go and check the demo over there. Let me play the video. Inas, please let me know if the video is being displayed over there.
Yes, sir. We can see the video.
Yeah. So let me explain what the step by step what we are trying to do is. As you can see, this is kind of a IP camera, and it has a few of the components. If by chance you happen to attend the previous seminar on the UART attack, we have referred this particular same camera to extract the firmware from the UART as well. But now let's go understand how the SPI attack will happen on the same part. Right? So it has a camera, and so this is basically the memory chip what we are referring. This is the SPI chip, SPI flash basically. Now the next part is like, so we want to remove this, like, so this is the camera from where we have removed it, and the removed chip is basically soldered on some of the general purpose PCB. So you can see this EXPLIoT general purpose PCB where we have soldered these pins. So you can see there are 8 pins, and we have just soldered that according to the sequence mentioned by the datasheet, and to the align with this actually the PCBs over there. So we'll be using now this EXPLIoT Nano to be connected to this memory. Yes. So you need basically these 4 wires. Rather more wires, because you need to connect that hold pin as well, and write protect pin as well.
Can I ask a question?
Not right now. Keep your questions. You can write your questions on the chat box, and we will answer it at the end of the webinar.
All right.
So isn't it connected? So your hardware is ready now. Plug in your EXPLIoT Nano here in your USB part, and you can see now we're able to access this. Now what we're trying to do is we'll use the EXPLIoT the framework to access this particular chip. So these are, if you just put a list command, you can see the typical interfaces that EXPLIoT supports. Right, there's ATAC, CAN, the MQTT. Then you can have this I2C and SPI part as well. Right, BLE part. So now, since we know this is particularly the SPI communication, we want to use this SPI read part and the write part. So if we want to read the firmware, I'll use a read flash. I want to write something, I'll use a write flash. It shows basically kind of address and those things that you want to check out, the frequency at which you want to work. And here in EXPLIoT, we have made it simple, meaning like now we are reading this particular flash and now writing this to our system. So as you can see on this particular screen, that it shows that what was the actual chip over here. You can see Macronix MX25E0664. It's a 8 megabits bytes of memory. It gives its frequency, its size, everything, right? And it is now reading the data over there, right? It shows the past. Now, this particular binary has been stored. So it shows the read flash has been passed. Now we'll go to our system. And we'll use kind of since we have this particular binary, it's time to kind of do the analysis on particular binary, right? So there are utility called as a binwalk utility, which help you to do that as well. So we'll be using it. So the capital E here stands for the entropy. So we'll try to see how well encrypted your firmware is. So this was the binary that we have found out. So you can see some percentage of encryption and those part over here. Let's move further. Now, if you just put it in small e, what we'll do is it will extract your binary. And let me pause over here. As you can see, this particular binary has been extracted. You'll able to see the file system part, right? So the address over there, and you can see there is a squash FS file system over there with a little Indian format. Now it's time to go and find this detail, right? So what will happen is once you extract this particular SPI camera bin, you'll able to see the folder that has been generated with the same extracted firmware name. And inside this, you can see this particular folder about squash FS root. So we'll get the details about the system as well. So let's go into that squash FS. So this is a typical Linux file system. And let's say I want to, since this is a IP embedded camera, I want to, let's say, find out the credentials about the Wi-Fi. Let's find out that. So when you go to the ETC, you'll able to find that the WPS applicants. So in this particular configuration, WP_conf, right, you'll able to see this particular credentials of this, right? So that way we can find the details about the credentials of this particular device from the extracting the memory. So this is one of the attacks on this SPI part, right? So yeah, so that's what it is, right? So that's it from my side, right? Thank you very much. Now we can take questions.
Thank you so much, Mr. Yashodhan. Let's move on to Q&A, everyone. You can ask your question in the chat box. I think we already have one. And I guess it has been answered. The question was, EXPLIoT Nano is a pair of two devices. It's a no.
Pair of no, it's a single device. It's a single device, as like you can connect this particular single device to multiple peripherals. So either you want to have a attack on the UART or SPR or your ZTAG, you can use the single device, and with the combination of the pins, you can connect to those particular respective peripherals, and you can extract the data over there. It's single device.
Any other questions? So the question is, can you show the multi-purpose board where you soldered the SPI chip? Sir, you're on mute.
Yeah, I can show that as well. So that what actually we have designed internally. I can just show. Just give me a moment. I'll replay the video.
So do you want to share the screen? Yes. You're on mute. Mr. Yashodhan?
Yeah. Can you hear me now?
Yes, we can hear
Yeah.
you.
Can you see the video as well?
I can see the video. Yes, I can see the video.
Yeah. So this is basically the question asked, like this is the multi-purpose board where you have kind of the pinouts for what you call as a QFN and different packages over here. And eventually you can just extract and desolder your memory from your product, and you can solder it back. So basically the combination of the 8 pins or the 16 pins, that's what breakout board that we have created, and you can just extract and solder over there. So that's what actually it is.
Are you able to do the same with different flash packages, LGA, BGA, etc.?
Yeah. So as you can see over here is like we have these 2 packages. The BGA package, I don't believe we have that, but most of packages we have the standard package, QFN package, and those things are available with that.
Can we flash the extracted firmware back into the device using this Nano?
Yes, we can do that. Yes, we can do that. So with the same thing, whatever things, let me play it video again. So let me go to the next step where we had extracted it. Let me go back into that. Right, so you can see this command, right? SPI generic read flash and SPI generic write flash. So what we had done is like read flash. If you want to, let's say, do the reverse, let's say you extract the firmware, you manipulate something into that firmware, and now you want to put that into that memory chip, and again memory chip you want to solder back to the product. What you will do is do the reverse process where you use the write flash, you write it to the memory location, and do the rest of the stuff, right? You can do that.
We have one more question, sir. With EXPLIoT Nano, can we do the canvas sniffing?
Canvas sniffing is not here as of now. EXPLIoT tool framework has that capability, this framework, but not with Nano as.
Okay. EXPLIoT Nano automates the process of reading flash. If we do the attack without Nano, how do we identify the SPI speed?
Okay, so eventually if you want to go for finding out certain these things, like, so without using any tools, you'll have to look first where that SPI chip is, whether you are using a sensor, SPI sensors or the SPI flash, let's say, right? You see the part number of this particular flash, go to Google, find a data sheet, find out the pinouts of that, desolder it, then possibly you can have your own general purpose PCB, not general purpose, but kind of a breakout boards that you get with in a market, and you can solder that as well. And then on the similar way, you can use different tools like the flash ROM or something like that. You can connect to Raspberry Pi and you can extract that as well. But this is a very tedious process, I'll tell you. You'll have to create a lot of voltage, and those things are there. There are a lot of challenges. I'm very honest with that. Any other question, Nas?
No, there are no questions. I think we can conclude the webinar. Thank you, Mr. Yashodhan, for this insightful webinar, and thank you everyone for attending this.
Thank you everyone for the good questions. Thank you so much.
Thanks a lot, Patu.